Hello and welcome to session 209 in the AISafety.com reading group. Tonight we'll be discussing the second half of the slideshow Unpacking Classic AI Risk Arguments by Ben Garfinkel. Ben Garfinkel is a research fellow at the Future of Humanity Institute at the University of Oxford. This is uploaded at Google Docs, and it actually has two titles. In the slideshow, it's called Unpacking Classic Arguments for AI Risk, and the file is called Unpacking Classic AI Risk Arguments. There is no date in the text. You can see that 2018 is recent. We'll only be discussing the second half because the first half is actually, in my opinion, better presented in another Google document by Ben Garfinkel. Hopefully we'll get to that in a couple of weeks' time. It's unclear if this it's a slideshow. It's unclear if it's ever been presented to anyone. The title also contains the following: edited to add text. So I looked for comments. You can add comments to slideshows. I couldn't find any, and of course, if there are more comments to this or a recording of it somewhere, then of course I might. I haven't incorporated that, and I would probably have misunderstood a number of things. So I would, as always, really like to thank Ben Garfinkel for critically examining the arguments behind AI safety. I think that's really, really important, and possibly one of the most important things anyone should be doing right now. And let me just close this and go to the actual. I'm hitting the wrong buttons. And also another thing that in the podcast that Ben Garfinkel made, he he had a quote about AIs moving strawberries to plates, and I said that I couldn't find that, and it would be nice with a reference, and there is indeed a reference here. So thank you for finding that for me. Let's talk a bit about the orthogonality thesis. Here are two vectors that are orthogonal. That means that they have a right angle in between them. A common argument against AI safety is probably based in moral realism, in that if a system becomes intelligent enough, it will be good in that it will discover the universal moral laws, or it will be human-like. And as a counter argument for that, for the human-like morals, is the orthogonality thesis created by Nick Bostrom, that intelligence and final goals are orthogonal. More or less any level of intelligence could in principle be combined with more or less any final goal. And this is this orthogonality thesis is accepted by Ben Garfinkel. I actually do have a number of small problems with how it's presented, but I probably won't go into them here. And instead, I've tried to here formulate this in a more formal way. So this here means that for any combination of IQ, capability really, and goals, there exists a system such that the system has capabilities equal this level and a goal that is this final goal. So this should be a restatement of the orthogonality thesis. Now, Ben Garfinkel introduces the process orthogonality thesis. The process of imbuing a system with capabilities and the process of imbuing a system with goals are orthogonal. And so quantities, it's easy to see that two quantities can be orthogonal with like goals and intelligence. You have oranges and apples, and enough you can have any combination of those. But what does it precisely mean that two processes are orthogonal? Well, to clear this up, Ben Garfinkel has some quotes by Nick Bostrom and others, and it seems to be that first you create a generally capable system, and then you add a goal. So this doesn't really seem to be orthogonality, but more like seriality, in that first you do one thing and then you do another thing. It seems to be that there are two processes, and whether the processes need to be orthogonal or serial is a difference between the process orthogonality thesis and what Nick Bostrom is actually talking about. So here I've tried to actually formalize this. For any combination of IQ and goals, there exists a system and a decomposition into two processes, such that the system is decomposed into first process G and then process F, and process G gives it capabilities, and process F gives it goals. So you do first give it capabilities and then give it goal. So Benka-Finkel argues against this, and the way he tries to disprove this is by giving 4 examples of systems which are not process orthogonal. At least with my formalization, this is just logically invalid. You cannot prove that no such system can exist by giving 4 examples of non-process orthogonal systems. I believe that the process orthogonality thesis, as stated here, is almost certainly true, because this existence quantifier is really, really powerful, right? There must be any kind of system in principle possible. Then there are many, many systems that are in principle possible. It's possible that Benka-Finkel doesn't mean precisely this, but a stronger form, in that all systems that can be created through orthogonal processes. I think that's probably false, but I could see it being true actually. So it's not immediately obvious. This leads into a debate. At least I believe this leads into a debate about narrow and general AI, because the first 3 examples that Benka-Finkel gives are thermostats, Deep Blue, and OpenAI 5 that plays daughter. I believe that the reason why these are not process orthogonal are because these systems are narrow and not generally capable. The last example that Benka-Finkel brings up is the process by which the brain achieves capabilities and goals. So it doesn't say more than that it's illustrative. I think it's like it should not be illustrative, in that I expect that the process by which AI becomes more capable and get more goals are likely to be very different from how AIs do it. So how do humans actually get capabilities and goals? I guess if I should say that capability, we get some from biology, some from education, some from experience. How do we get our goals? Maybe indoctrination or cultural osmosis or morality. But this is probably, I've forgotten like 20 things. And I think worrying too much about this is likely to be a waste of time, in that we should expect that AIs are likely to be very different from humans, and this is actually precisely the point of the original orthogonality thesis. Benka-Finkel has an example of a non-process orthogonal system, which is the case of a house cleaning robot, and I'm not really fond of this kind of examples. It seems awfully naive to me, in that if we imagine that there is some kind of international race for building AGI, and states put a meaningful percentage of their resources towards winning this race, then what will they use it for? They'll use it for strategic effects and not for cleaning houses. It feels very silly to talk about. Benka-Finkel makes the following claims: that if you make really simple rewards functions like dust minimization, then that won't work. We don't have enough data for imitation learning, and existing reward modeling approaches are probably insufficient. So we need something like alignment. I think I would disagree. There are probably a lot of people who would say cleaning a house, that's AGI, but I think actually that this is something that does not in any way require any interesting methods. The hard part is building a robot. That's really hard. And the other hard part is to making this robot understand the world. But once we have that, then figuring out what actions you should take are probably really easy, at least comparatively easy, right? You can't literally solve it in 5 seconds by saying dust minimization, but if you spend like half an hour by the clock, you can probably get really far. So in order to really dig into the arguments for process orthogonality, Benka-Finkel, or actually more like Benka-Finkel later introduces the concept of measure-based arguments, and I will push that a bit forward to also use those in the context of process orthogonality. So a measure-based argument is that most possible AI systems in a certain set would have a certain property. So this is like a template for an argument, and the set and the property are something you fill in. A good example would be instrumental convergence, where the claim of the instrumental convergence thesis is that most possible AGIs are instrumentally convergent. So that would be an example of claim. And in order to argue against this, Ben Garfinkel outlines 3 strategies. The first is to say that the premise is false, that in fact most AGIs are not instrumental convergent. The second is that the premise might be true, but we won't build AIs within this system. We'll build from a larger system like comprehensive AI services or something like that. Another option for arguing against a measure-based argument is that, okay, we might be in this situation, but there is indeed another process that pushes us towards this. For instance, AI safety could be an example of a process that pushes us towards building an AGI that is indeed not instrumentally convergent. These Venn diagrams here are my interpretation of the slides. They're not from Ben Garfinkel, so it is in this point in particular quite possible that I've misunderstood him. So how does this apply to process orthogonality? Well, you could make the following claim. Most possible AI systems in the set of AIs likely to be built during the next couple of decades would not be process orthogonal. So this is me reformulating Ben's argument. And I hope I'm not strawmanning too much. I think this is what Ben Garfinkel is pointing towards, but I'm not 100% sure. And a big part of the argument is that we don't really see any process orthogonal AIs right now. And it looks like we won't see them in the future. And Eric Drexler basically states the same, but somewhat more forcefully. So that's an interesting question, right? The first AGI, where AGI is defined as something that can do everything a human can do, is that something that's going to be made through a process orthogonal system where we first give it capabilities and then give it a goal? Or is it going to be like in the service model where that's an amalgamation of 100 systems that each can do one thing that a human can do? Well, I think it's more likely that we'll have something general, but I recognize that it's certainly possible that in the future we'll have something like comprehensive AI services. Ben Garfinkel goes one step further in saying that this is an implicit assumption lying behind a lot of the AI risk debates, and I disagree. This is the question that is commonly formulated as whether we'll have narrow AI and when we'll have the first general AI, and this is something that has been discussed very, very much in the context of AI safety. And the classic AI risk arguments also doesn't focus so much on this measure with most possible AI systems, but more on the first AGI, when that comes and what will be the consequences of that. And this is a central part of the classic AI debate. So if systems are not process orthogonal, what strategic implications can we draw from this? Ben Garfinkel is optimistic, saying that, well, if we can't get the goals right, then it will stop us from having good capabilities, and that means there won't be as much of a deadline as is implied in the full process orthogonality, where we have a system and then when it's ready, we need to give it a goal. There could be still as much of a deadline in that it is indeed possible to imagine an AI catastrophe with only a narrow AI. But there is also an argument that the degree of entanglement could make the deadline tighter, in that we can't wait with figuring out the goal until the capability work is done. It might be that we need to make the AI align even earlier. And part of this, the reason why might be that if we have a system that is unaligned at some point, and then later as it becomes more capable, we also want to align it. But if it has at some point been unaligned, it probably doesn't want to become aligned, and that could be a real headache. Another measure-based argument, there are 4 in total, is on the complexity of value thesis. Roughly, most or all systems that behave like sufficient effective maximizers of simple utilities functions are dangerous. I'm not really fond of this way of putting it, because if you put the word sufficiently, then it easily results in things that are tautologically true. And also the way I would formulate this instead is by using the decisive strategic advantage, which is indeed how, for instance, Bostrom does in the book Superintelligence. This is a case where the premise might be true, but we won't tend to create systems in the relevant set. We'll do something else like comprehensive AI services. And kind of maybe a concrete counterexample could be GPT-3, which is our most powerful and most general AI, and the goal is basically predict the next word. So that's an argument why we might do this. And Ben Garfinkel finds it unnatural to think that we'll build powerful and destructive AIs with simple utility functions, and because this is dangerous. And I think this is because people, whether this will happen depends on to what extent people care about AI safety, but it's a circular argument to say that you shouldn't worry about AI safety because we won't do anything dangerous because people are worried about AI safety. In my previous 2 videos on Ben Garfinkel, I did in the first one, I elaborated on this point quite a bit. As a third measure-based argument is on the fragility of values thesis, which roughly says most or all systems that behave like sufficient effective maximizers of utility functions slightly different from benign ones are dangerous. And Ben Garfinkel says that he believes this is false, or he's sympathetic to saying that this is false, but doesn't say more really. So he's not really unpacking arguments. I won't really go into details here. I can't go into details here. Lastly, we have instrumental convergence, which Ben Garfinkel spends quite a bit of energy arguing that it's a measure-based argument, which I believe it almost is. And the statement is that many or most possible AI systems in a certain set would have an inclination to commit omnicide for instrumental reasons. This set could be one of, he gives a number of suggestions for what the set could be, and points out that there are a lot of possible AI systems which are not, don't have this instrumental convergence. I believe it's true, but when we're talking about infinite sets, then it doesn't prove a lot to say that there are a lot of systems in this infinite set which don't have a property, because there might be many more that do have this property. So what are the arguments against instrumental convergence? By the way, I love this picture. I think it's really neat. Well, these kind of measure-based arguments, if you try to apply them to existing technologies, then they fail. And this is something that people who argue for AI risk would readily admit, that the risks from superintelligence are qualitatively dangerous from the risks from most other technologies like self-driving cars. And the reason why these fail, these kind of measure-based arguments, is because there is a process by which we create these technologies where we try to build artifacts that are useful and safe. And the problem with this argument is that we don't have such an engineering process. So it's not enough to just have good intentions in order to build a safe system. You need to actually have a way to do that. And if you don't have a way to build an aligned AI, well, then you will just pick an AI at random that's capable and hope it will be aligned. And when you pick one system out of randomly, then the density of dangerous designs compared to benign designs matters a lot. And that's the measure-based argument. Also here, I would say that I believe the unpacking that Ben Garfinkel is doing is quite valuable. He has an example here, an analogy with the utility function that he has for his surroundings. And it seems that there are many ways you could imagine you want your surroundings, but evolution has just picked out a reasonably good one for him. And the way I would respond to this is that it's actually a really simple problem. You could imagine this is a classic stability where you have a ball in a bowl. And this is the kind of problems that can be solved by a greedy algorithm, like evolution. And some problems can be solved easily, but there are also harder problems. And I want to give an analogy with why I believe that AI safety is a harder problem. So the analogy I'm going to be using is with software bugs, where I'm going to argue we are in this case where the ball is inverted and the ball is on top of it. So, of course, this might be reference class tennis that I'm playing here, in that I respond to an analogy with another analogy. But let me try. With a personal story, when I was something like 20 years ago at the university, I made an operating system as part of a course, really, really simple. And if you try to run software on that operating system and you made any kind of error, like at all, then your software did random things. And software errors are basically the CPU doing random instructions. And when you don't have an operating system that can protect you from yourself, like mine obviously didn't have, then just about any bit that is flipped turns the program into a complete disaster, right? If you want to jump to a particular address and you get that anything other than 100% correct, then you're going to have not just a tiny error, but cascading errors that will bring down your computer and corrupt everything. So that's a measure-based argument. Most possible software systems that are adjacent, even one bit away from the software that someone like me would try to create on an operating system that doesn't have these safety measures, will fail catastrophically. Now, why do I believe this is a good or important analogy? Well, software errors is a strict superset of AI risk, because AIs are software and AI risk is likely to be an error. But software errors is an area that has been studied really, really well, especially compared to AI alignment. And when we build software, we have built an enormous amount of type systems and memory isolation and all these kind of things that mean that when we actually build software, we don't have to, it doesn't feel quite as difficult as it actually is. The most important guardrail we have is software testing. That's the key way to avoid software errors. And that is, unfortunately, one thing we can't use for alignment because of the treacherous turn. So that means that AGI would have to be the first ever, probably, large, correct, untested program. And we have no really way of reasoning in a principled way about what correctness actually means. And that is my measure-based argument for why we should expect that the first superintelligence or AGI will fail catastrophically. That is all for today. Thank you and see you.